Download this code from codegive.com, link in the description below. OK, let's dive deep into disk formatting, directory structures, and explore some related concepts in the context of operating systems. I'll provide a comprehensive tutorial with examples, focusing on concepts relevant to understanding how operating systems, like those studied in a KTU syllabus, handle these tasks. Keep in mind that this is a broad topic, and the depth of implementation details will vary depending on the specific OS and file system in question. I will focus on illustrating the core principles. Understanding disk formatting. Disk formatting is the process of preparing a storage device, like a hard drive, SSD, USB drive, etc., for use by an operating system. It involves several key steps. 1. Low-level formatting, LLF/physical formatting, rarely done by users anymore. This is the most basic level of formatting. It defines the physical structure of the disk. This includes tracks, concentric circles on the disk surface, sectors, pie-shaped wedges dividing each track. Historically, sectors were 512 bytes, but newer drives often use 4096 byte sectors, 4K sectors, for efficiency. Cylinders, a set of tracks at the same radial position on all disk surfaces, if the disk has multiple platters. Gaps, small spaces between sectors to allow for head switching and synchronization. Modern drives usually come pre-formatted at the low level by the manufacturer. Low-level formatting is usually only done by the manufacturer or with specialized tools. It is generally not something users do on a regular basis. Doing it incorrectly can damage the drive. 2. Partitioning. This divides the disk into one or more logical sections called partitions. Each partition can then be formatted independently. A partition table, example master boot record, MBR, or GUID partition table, GPT, stores information about the partitions, such as their start and end sectors, type, and bootability. Common partition types include primary partitions. MBR allows for a maximum of 4 primary partitions. Extended partition. One of the primary partitions can be designated as an extended partition. An extended partition can contain multiple logical drives. This allows you to overcome the 4 primary partition limit. Logical drives. These are partitions within the extended partition. 3. High-level formatting / logical formatting. This is the step that creates the file system on a partition. It writes the file system's data structures to the partition, including boot sector. A small section at the beginning of the partition that contains code to boot the operating system, if the partition is bootable, and information about the file system. File system metadata. Structures that manage files and directories, such as file allocation tables, FATs used in FAT file systems, FAT16, FAT32. Nodes, index nodes used in Unix-like file systems, ext2, ext3, ext4, etc. Master file table, MFT used in NTFS. Root directory. The top-level directory of the file system. Free space management. Mechanisms to track which blocks on the disk are free and available for storing new files. This may involve bitmaps or linked lists of free blocks. 2. File systems, organizing data. A file system is a method of organizing and storing data on a storage device. It defines how files are named, stored, retrieved, and updated. Different operating systems support different file systems. Here are some common file systems. *FAT, FAT16, FAT32. *Early file systems, widely used in DOS and early versions of Windows. Simple but have limitations on file size and partition size. *FAT uses a file allocation table, FAT, to track the allocation of disk blocks to files. The FAT is a table that maps each cluster, a group of sectors, to either the next cluster in a file or a special value indicating the end of the file. The root directory has a fixed size, which limits the number of files that can be stored in the root directory. *NTFS, New Technology File System. The primary file system used by modern Windows operating systems. Supports large file sizes, security features, access control lists, journaling, for reliability, and other advanced features. NTFS uses a master file table, MFT, to store metadata about files and directories. The MFT is a database-like structure that contains records for each file and directory on the volume. EXT2, EXT3, EXT4, Extended File Systems. Commonly used in Linux. EXT4 is the most recent and widely used version. EXT3 added journaling to EXT2. EXT4 improves upon EXT3 with features like larger file systems, extents, and improved performance. These file systems use inodes to store metadata about files. An inode contains information such as the file's size, permissions, timestamps, and a list of data blocks that contain the file's contents. HFS Plus, Hierarchical File System Plus. Used by Mac OS. Supports metadata, journaling, and other advanced features. APFS, Apple File System. The modern file system used by Mac OS, iOS, and other Apple devices. Designed for SSDs and flash storage, with features like snapshots, cloning, and space sharing. XFS*. A high-performance journaling file system originally developed by SGI. Now commonly used in Linux, especially for large storage systems. 3. Directory structures, organizing files. A directory, also known as a folder, is a special type of file that contains a list of other files and directories. Directories are used to organize files into a hierarchical structure, making it easier to find and manage them. Hierarchical structure. Most operating systems use a hierarchical directory structure, a tree-like structure, to organize files. The top-level directory is called the root directory. Directories can contain subdirectories, creating a nested structure. Pathnames. A pathname specifies the location of a file or directory within the file system hierarchy. Absolute pathname. Starts from the root directory and specifies the complete path to the file or directory. In Unix-like systems, the root directory is represented by /. In Windows, it's a drive letter followed by a colon and a backslash, example see backslash. Example, /home/user/documents/report.txt, Linux, see /user/documents/report.txt, Windows. Relative pathname. Specifies the location of a file or directory relative to the current working directory. If the current directory is /home/user, then the relative pathname documents/report.txt refers to the same file as the absolute pathname /home/user/documents/report.txt. Directory entries. Each directory contains directory entries for the files and subdirectories within it. A directory entry typically contains asterisk the name of the file or directory, asterisk a pointer to the file's metadata, example the inode number in ext file systems or the MFT record number in NTFS. 4. KTUOS concepts and code examples, illustrative. While a full-fledged OS implementation is beyond the scope of this tutorial, we can illustrate some key concepts with simplified code examples. These examples will be written in C, as it's a common language for operating system development. These are simplified examples and are not intended to be directly used in a real OS. A. Simulated disk structure. First, let's simulate a simplified disk structure in memory. We'll use a simple array to represent the disk blocks. B. Simulating file creation. C. Simulating writing to a file. D. Simulating reading from a file. E. Simulating directory structure, very basic. This example lacks a true directory structure. To simulate one, you'd need to 1. Treat directories as special files. 2. Store directory entries, file name, inode/block number, within the data of the directory file. 3. Implement functions to create directories, list directory contents, and navigate the directory structure. F. Main function, example usage. KTUOS specific considerations. When studying these concepts in a KTUOS course, you might encounter questions or assignments that focus on asterisk file system design. Asterisk you might be asked to design a simple file system, specifying the data structures used for inode/fat entries, directory entries, and free space management. Asterisk disk scheduling algorithms. Asterisk how the OS decides the order in which to access disk blocks to optimize performance, example FIFO, SSTF, scan, cscan, look, clook. Asterisk memory management. Asterisk how the OS caches disk blocks in memory to improve performance. Asterisk file system operations. Asterisk implementations of system calls like open, read, write, create, delete, mkdir, remdir. Asterisk concurrency and locking. Asterisk how the OS ensures that multiple processes can access the file system safely and consistently. Asterisk recovery. Asterisk how the OS recovers from crashes and ensures file system integrity, journaling, checksums. 6. Key takeaways. Asterisk disk formatting is a multi-stage process to prepare a storage device for use by an OS. Asterisk file systems provide a structured way to organize and access data on the disk. Asterisk directory structures allow for hierarchical organization of files. Asterisk operating systems manage disk space, file metadata, and directory structures to provide a user-friendly and efficient file storage system. Asterisk understanding the underlying principles of disk formatting and file systems is crucial for operating system development and understanding how data is stored and managed on computer systems. Remember that this is a simplified overview. Real file systems are significantly more complex and involve a great deal of optimization and error handling. Consult your KTUOS course materials and textbooks for more detailed information and specific requirements for your curriculum. Good luck.